Welcome back, stat friends. So in part one of this video, we tested random slopes. So we learned how to run and interpret random slopes models in a multi-modeling framework. And so that left us off with about here in our handout, which was where we evaluated the combination of two random slopes in a model if that was beneficial. So now we're going to do something a little more fancy, but that I think is really, really good. So and really useful. So we're going to talk about how to model a cross-level interaction. So last week, I think we looked at an interaction between two level 1 covariates, which was lead and t-sig. And I showed how to model that. And that's actually very much like any sort of an interaction in a regular regression model. But now we're going to do one that's a little bit more complicated, and that is we're going to model an interaction between a level 1 predictor and a level 2 predictor. And in this case, we're going to look at an interaction between individual task significance and group task significance. And another way to put this, I mentioned this in the handout, is there an interaction between how I feel about the importance of my job and how my peers feel about the importance of their job? Probably, right? And so does one shape the relationship of the other with our outcome, which is hostility? So it's definitely something you would be worth testing. Again, this is an icing on the cake kind of method. You would look at this after you would explore main effects models, maybe even after you've explored the inclusion of random effects. So this is kind of a last step in your investigation. But remember, a lot of times, particularly questions about subgroups, to think about this from kind of a quant crit perspective. If we're interested in subgroups, we need to use interactions to understand if those subgroups are functioning differently relative to other groups. And so if we want to look at economically disadvantaged students, or if we want to investigate the relationship that particular groups of students from different racial or ethnic backgrounds have with an outcome, we need to use interactions. So we need to get good at this, and it's something, it may not just be icing on the cake. It might actually be kind of a foundational theory about what you want to test in your models. So the first thing we need to do, we need to learn about centering predictors, and you may or may not have learned about this before. So what does it mean to center? Centering a variable basically means you subtract the mean score from every observation. So to use an example, if we centered our variable hostility has a mean of something like 2 point something on a scale of 1 to 5. So the average person rates about 2 on a hostility scale in this data set. If we were to center that variable, we would subtract that mean from every observation. So if I was at the mean, my score would no longer be 2.2, for example. My score would be 0. If I was below the mean, my score would be negative. And if I was above the mean, my score would be positive. And it is a good idea. And really, anytime you look at interaction effects with continuous variables, it's usually a good idea to center all your predictors before you analyze it. The reason being, it won't change the p-value, but it can change the estimate itself and its interpretation. And so it's a lot easier to just center everything beforehand and make sure that that's taken care of. Now, last week we tried this without centering. That can be okay just as a test. But if you're really getting serious about looking at moderator analysis and interaction effects, it's a good idea to center. Okay, so how does this work? Again, we're going back to our friend dplyr, and we're going to use the mutate function again. And we're essentially creating a new variable that is equal to the original variable minus its mean. And we get that using the mean function. So it's not too bad. And then we can check our work using the psych function to make sure that this makes sense. So here's the code for that. I create a new data set for this. Again, it could be overkill, but for storage is cheap. We have really big, fast computers, and adding another copy of this data set in the memory for now is not going to hurt it. So I'm going to create a new data set called LQ2002.2, which is going to be the data set I use for moderator analysis. And I'm going to start with 0.1, which was the data set I created earlier. And then, right, pipe operator, I'm going to mutate, which means I'm going to create new variables from existing ones. And I'm going to create a variable called tsig_cent for centered. And that's going to be equal to the original task significance score for each person minus the grand mean of task significance score. So the average of task significance across the whole sample. Then I'm going to put a comma, because the cool thing is you can do a bunch of these in a row. I'm going to create a new variable called gtsig_cent. So this is task significance at the company level. And that's going to be equal to gtsig minus the mean of gtsig. So now I've basically taken two predictors that I want to use and I've centered them out so I can use them in an interaction. So I'll run just that line. And again, if you press Control Return, it'll just run one line for you. And now I have a new data set called LQ2002.2. And if I click on it in View, I should have a couple new variables at the end, and I do tsig_cent and gtsig_cent. And then I'm going to use the psych function to describe this. And I put fast equals true here because I don't need all the statistics that you get with describe. I just want to know what the mean is, essentially, and a couple other things. So again, this is lazy loading. I mentioned this last time. So because I don't want to load the whole psych package, because I'm just going to use it for this, I'm just going to type psych and then 2 colons, so it knows I want to use the psych package and I want to use this specific function. And then I get my results. And so here are the variables I've seen already. I'm going to keep clicking to get to the ones at the bottom. So here is tsig_cent and gtsig_cent, and notice they both have mean of 0, which is what I want. That means they're centered. And the min for tsig is about -2, and the max is about +2, and the range is 4 almost exactly. And for gtsig, this is my group measure of task significance. Again, the mean is 0, and the min is about -0.5, and the max is about 0.5 or 0.6, so the range there is quite a bit shorter. And that makes sense, because when you take the average of something, you tend to sort of regress to the mean, right? You shrink in the outliers. So it makes sense that the group average measure of this has less variability than the individual measure. Okay, so that's step 1. And again, you would do this for any continuous variable that you want to include in an interaction. In this case, specifically, we're doing a cross-level interaction. So we're interacting a level 1 predictor with a level 2 predictor. But you would do this even when you were interacting variables on the same level. Okay, so step 2, once you have your centered predictors, is to run a model, what I call a main effects model. So this is a model that does not include the interaction term, but only includes your new centered variables as main effects, because we need that as a baseline. So I call this model.4 because I ran 3 models earlier testing random slopes. You can call it whatever you want. And notice it's the same model that we ran above as our sort of main model, except for instead of tsig, I now have my centered tsig, and instead of gtsig, I now have my centered version of that. And notice I have my new data set, LQ2002.2, because that's the one that actually has these new variables in it. You might ask, do I need to center lead? The answer to that is no, if lead is not going to be included in an interaction. So if a variable is not included in an interaction, it's not essential that it's centered. If it is a continuous variable that's going to be in an interaction, you do need to do that ahead of time. Okay, and then I get a model summary here. So this is my main effects model. This gives me a nice baseline, AIC and BIC, which I can use to figure out whether or not I should keep my interaction, which I'm going to run below. And then I get my estimates here. And notice, I think these are actually identical point estimates to what we got when we ran this with tsig and gtsig. The reason being, when you center something, you don't actually fundamentally change the distribution of the variable. You just move it up and down along a plane. And so we're not actually changing the distribution of scores. We're just changing the underlying starting point. And so those estimates are not going to change at all. We could center it on 100 or 0 or any number of things. Okay, so that's our main effects model. And then I'm going to give this a title, Interaction Effects Model. So here's our interaction effects model. So it looks almost identical. I'm going to give it another name, model.5. The only difference is on the end of this, I've now added the interaction between t-sig cent and gt-sig cent. I like using the colon. You can also use a asterisk to denote an interaction, whatever's easiest for you to remember. And everything else is the same. And then we look at our results. And so notice it's interesting. We get AIC and BIC. Looks like AIC went down a little bit. That's a good sign. I'm not sure what BIC did. BIC was 5567 and it's 5569. Okay, so this is a mixed kind of conflicted information kind of thing, which is good. That happens a lot in this kind of work. And then we have our interaction here. So here are our main effects, and then here is our interaction effect. And I think I've mentioned this before, but just a reminder, when you're testing interactions, focus on interpreting the interaction. Do not pay much attention to the estimate or the significance of the main effects, because the main effects fundamentally change once you introduce an interaction into the model. If you have an interaction, that's really your story. That's the exciting part. And in our case, it looks like we might have something. It's a positive interaction between these two things. And here's the estimate, 0.15. It's standard error, and our t-value is 2.33. So if we assume our cutoff is about 2 for a t-statistic, this is above that. And so this may be a significant interaction that we want to include. I'll show you in a moment how to get an actual p-value for this that you can rely on. But it's actually really interesting. So, okay, so a positive interaction between these two things. What exactly does that mean? Well, it means that, let's use the example of an individual. An individual with a higher task significance score is also is going to be associated. See, it's even tricky for me. Is going to be associated with a group task significance score slope that is also more positive. So as one goes up, the slope of the other goes up. So as task significance individually goes up, the slope of GT sig goes up. And as individual scores go down, the slope of GT sig also would be expected to go down. That's a little hard to interpret in this case because going up is not necessarily a good thing, because hostility is something we're trying to avoid in this research if we can. So as usual, those interactions are so pesky and hard to interpret. But I'll show you in step 3 how to use an interaction visualization strategy like we did a couple weeks ago to make this hopefully a little bit easier. Okay, so before we do that, we should probably ask the question, can we get a p-value for this interaction before we spend too much time thinking about whether or not it's significant? And our friend here to do that is the ANOVA command. And that is just going to compare the fit statistics for model 5, which includes the interaction term, with the fit statistics for model 4, which do not. And it's going to tell us whether or not there's a significant difference or an improvement in the model from model 5 to model 4. And sure enough, so I like this. It gives you a little summary. So here's model 4, no interaction. Here's model 5 with our interaction. And then the comparison, there's 1 degree of freedom difference in that one thing that we're estimating. That one parameter that we're estimating is our interaction effect. And by adding it, we get a model improvement. We go from a AIC of 33 to 30. BIC goes up, right? So we get sort of conflicted information. But when we calculate a chi-square for this, it's about 5 points, and it's barely significant, but it's there. So this is the p-value for the interaction effect, 0.02. So we would want to consider it based on the evidence here. Okay, so if we're going to use this thing, we should probably figure out what we're going to do. So how are we going to visualize this and make some sense out of it? I recommend using this package called Interplot. I talked about this a couple weeks ago in my page on going deeper with interaction effects. I think that it's a very useful way to compare values. I talk about margins here. You may not see this in your version. So margins is stata talk. So Interplot is what we need to use as our users. So I'm going to do this lazy loading trick again. So Interplot is the name of the package, and I'm actually calling the Interplot function. So it's a little confusing. It's actually a function that has the same name as the package. But I'm calling Interplot, and I want to apply that to model.5, which is the model that includes the interaction. And then I just need to tell it what var1 is and what var2 is. var1 is the variable that is the target of moderation, and var2 is the variable that does the moderating. Now, I'll say that again. So var1 is the target of moderation, and var2 is the variable that does the moderating. In terms of the math, you can flip these and you get the same exact interpretation. It's just in reverse. So that's totally up to you as a researcher as to what variable actually is moderating the other. We can't tell a difference in direction based on a model like this. But for our purposes, I'm going to say, okay, how does the slope, that's what var1 is going to give you, how does the slope of GT-sig change according to individual T-sig scores? So how does the impact of GT-sig on hostility change according to individual scores? That's one way to think about it. And I run that, and it does some thinking. Maybe a lot of thinking. There we go, and we get a plot. Okay, so we have to refresh our memory a little bit. So var1 is over here. It's on the left side. So this estimate over here on the left side is the slope of GT-sig. And this representation down here, this is the individual value of T-sig. Okay? So I always like to just look across the range of things here. So the slope estimate for GT-sig is going to be highest, or have the most impact on hostility. It's going to be the most negative, because in this case we want to reduce hostility, so we want a negative slope. So the slope of GT-sig is the most negative for someone who has the lowest task significance score. So this is someone who is, so 0 is the average, because we centered this. So someone who is 2 points below average. So this is somebody who is not super happy about the significance of their job or their task. For somebody like that, the group has a really big impact. It actually has the largest impact. Okay? For somebody at the mean score of task significance up here, the group still has an impact on reducing hostility. Again, negative slopes means hostility is going down. So the impact of the group is still important here, but not as important as when you are someone who has the lowest sense of task significance. Okay? Now, going to someone with the highest task significance, there it appears the group does not matter very much, because this estimate is basically 0, and the confidence interval, which is this gray thing, is on either side of 0. So interestingly, if you're telling a story, what story is it? Well, the impact of the group matters, but it matters most for people with low levels of task significance. So if you have folks with low levels of task significance, the impact of the group really means a lot. And that's the story, right? That's a really interesting story that you can start to tell about the interaction between those two variables. Alrighty? A couple other little things. So I love a good summary of models. And so here I just load up the model summary package. And it requires this package called Broom Mixed, which I'm also going to add. And then, so I might as well just load those in now. Now, and I would like to build a list of my models because I want to put these into a little summary table. So to do that, you call something models and you name it as a list. And I'm going to include just model 4 and model 5 because those are the last two I ran, and I have the main effects model and the interaction. And so I'm going to run that, and then I should get a new, there we go. So I have a new thing called models. And then I'm going to, actually I'm going to run this. There we go. It didn't run quite right. So now I have a new thing called models, which is a list of 2. And then I'm going to make a model summary from that list. And here I say output equals markdown. This is just to give you a nice clean looking table on the bottom here. And there's our result. So here's model 1. So here's our AIC, BIC log likelihood. Here's model 2. The difference is the T-sig by GT-sig interaction, which pops in right here. And then you can kind of compare straight across how things change. And this looks really great. You can copy and paste it into a Word file. I even include some code down here for making a HTML table if you want. So again, I always think it's a good idea to create summary tables of this stuff and as quickly as possible get it into APA format or something that you can work with. So okay, I think that's it. That's the last demonstration, our demonstration for Module 5. Hopefully that makes sense, and good luck.